So this is the title. I'll be talking about algorithmically random infinite structures. So here's the plan. So I'll what? So I'll explain the concept of branching classes. I'll say a few words about Martin-Löf randomness, computable structures and randomness, algorithmically random, computably enumerable, and co-computably enumerable structures, degrees of Martin-Löf random structures, and measures of varieties. So this is the topics. You can interrupt me anytime you want, ask questions, don't hesitate. So here's the literature. So this is the Logic in Computer Science conference proceedings. I think I want to say that this is one of the computer science conference proceedings where conferences quite competitive, but where actually computability is appreciated. So that's a good venue for us to publish. So Quest for Algorithmically Random Infinite Structures, proceedings of LFCS. Sorry? Quantifier, that's a mistake, sorry. So quantifier free definability on infinite structures. Quantifier, yeah, sorry. Yeah, so, and yeah, on infinite, anyway. And computability theoretic properties of algorithmic random structures. It's in preparation with Dan. So a little bit of motivation. So we know that the history is fascinating. It goes back to the work of Kolmogorov, Martin-Löf, Chaitin, Schnorr, and Levin. And the last 2 decades have witnessed significant advances in the area. So there are 2 monographs as an example. There are many, many notions of randomness, techniques, and ideas. And when we introduce randomness, one of the important points here is that there is a measure on the Cantor space. So the measure plays a really important role. And the randomness, one of the ways to define randomness is through effective measure zero set. So that is string alpha is algorithmically random if no effective measure zero set contains it. So, and a set V, a collection of infinite paths in a counter space has effective measure zero if it is contained in an embedded sequence of open sets such that each Mi is an open set. Given an I uniformly on I, you can actually enumerate all the bases of the open sets that form Mi, and the measure of Mi is less than 1 divided 2 to the I. And such sequences are called Martin-Löf tests. So the measure is important. I'm not going to explain what it means. We all know more or less. So there are many nice philosophy behind these definitions. So here's the question. So the motivating question is, what is an algorithmically random infinite algebraic structure? So in 2000, I was talking to Rod, and I asked what would be a good definition, and his answer was, well, I don't know. So we need to have a good measure in the class of structures. And I've talked to Cheetat and Andre Nies. With Andre, we wrote we had the Marston grant. One of the topics were there we listed as algorithmically random structures, infinite structures. So basically the question is, how do you define a measure on a class of structures? So it turns out it is possible, and I'm going to give you some sort of axiomatic approach to define the concept of, to define measures on classes of structures. So what do we expect from algorithmically random structures? So these are all sort of a little bit informal, and each of them requires some kind of formalization. So the first natural thing is that continuum. We would like random structures to be in abundance, so the continuum. And this is the property of collective, which goes back, the notion which goes back to von Mises. Unpredictability, again, so it depends how you define it, but very informally, it means that there should be no effective way to describe the isomorphism type of the structure. So the question is what it means to describe. It is up to us to define. Lack of axiomatization, for instance, no simple set of first order formulas, for instance, universal formulas, can describe the structure again, or can define the structure. Again, the question is, what does it mean to define? So, well, I'll be answering all these questions in one or another way. And another important property, I would like algorithmic randomness to be isomorphism invariant property. I wouldn't like the algorithmic randomness to be dependent on the presentation of the structure. Right? So these are sort of quite informal explanation, so what we expect from algorithmic random structures. But even with that, so you come up with many, many immediate questions, right? So take a structure, code the structure as an infinite binary string. For instance, why don't we code the structure into string and transform algorithmic randomness for strings into structures? So that's a very natural approach. Or another question is, can a computable structure be algorithmically random? So the first intuition is that probably no, but I'll talk about that as well. So algorithmically random strings, for instance, they possess immunity property, and there is no infinite subsequence, computable subsequence of infinite subsequence of in a Martin-Löf random string. So the question is, do we have immunity-like properties in structures? So can a finite presentable structures be algorithmically random? So for instance, I'll give you a group, finitely presented group. Can the algorithmically presented group be random? So all these things, so natural questions, and I'm going to answer these questions in this talk. So, but first I would like to give you a very simple explanation why converting to strings doesn't give us a satisfactory answer. So let's assume for the simplicity, we're given a graph, right? So instead of graph, it can be any algebraic structure, any relational structure. So you list all the pairs, an infinite sequence, and so you have the first position, the second position, and the positions are pairs. And at position I, you put 1 if the pair ij is an edge. Otherwise, you put 0, and you converted the graph into a string. And now you can naturally give it the following definition. The graph is string random if the string that represents it is Martin-Löf random. So this definition obviously depends on presentation. So now, what I want to do is I want to connect the string randomness with the model theoretic randomness, which is known in model theory. So that's the concept of randomness by Erdos. So take the domain. The domain is sort of natural numbers. We all more or less know this construction. Take pair ij and put an edge between them at random. Right? This determines an infinite graph, and the resulting graph is called random graph. And it was known long, 30, 40 years ago, so that with probability 1, any two random graph is, the graphs are isomorphic. And this theorem, so Erdos and Spencer actually write, so if you read their paper, they say that demolishes this theorem, this result demolishes the theory of infinite random graphs. And the reason for that is its uniqueness property. So you have only, yes?
Why is it called a random graph?
Sorry?
Why is it called a random graph?
Oh, there are many reasons for that.
You didn't to ask the Erdos.
Yeah. It's called, well, I mean, so you're constructing by randomly. So my view is you can take pair ij, flip a coin, depending on the outcome, you put an edge or not. So you're constructing graph randomly. At the limit stage, you get a graph. It's called random. I mean, in a sense, it's a random graph. And with probability 1, it's all of them isomorphic. So and this interesting property. So one of the properties, we would like randomness to be in abundance. We would like to have continually many random structures. But this is already sort of contradicts to what we have. But it turns out any string random structure is random. That is, if you take graph, code it up as a string. If the string is random, then the graph is rado-random. So in particular, it implies that any two string random graphs are isomorphic. So immediately you kill the property you want, so the abundance property, continuity. The first order theory of the graph is decidable. So you actually described in the isomorphism type. The theory is omega categorical of this graph. So if you have a full description, the string random graph is axiomatized by extension axioms. That's any countable infinite graph can be embedded into G. So that's basically you're describing. You can live inside of the graph and walk and do whatever you want to do, basically. So it's So all this basically defy our intuition that we postulated for algorithmically random structures. So now what I'm going to do is I'm going to give some kind of axiomatization how to define randomness for structures. It's going to be not too hard. It's going to be easy. So I'm going to employ the concept of embedded system. So you have a sequence of finite structures, A0, A1, A2, and their embeddings. So each AI is a finite structure, and each Fi is embedding from AI into AI plus 1. And this is called the embedded sequence. And the sequence, so the underlying sequence is the base of the system. And obviously, every embedded system determines the limit structure. But the point here is, by varying embeddings, the limit structure, you vary the limit structure. So for instance, any countable linear order can be represented. So suppose AI is a linear order of size I. By basically varying the embeddings, you can get any countable linear order. So the limit here is dependent on the embeddings. So what I want to do is I want the limit not to be dependent on the embeddings. And so that's what I want to postulate. An embedded system is called strict if its limit, the direct limit of the system, does not depend on Fi. So they're always the same. Okay. And you can imagine there are lots of examples of strict embedded systems. So it's in a sense what I'm doing is I'm doing the approximation to the limit. And you can think of each AI as rational numbers, which are approaching some limit, which is a structure. So now I'm going to give lots of examples of classes of structures where the embedded systems are strict. And for that, I'm going to define. So this is a simple definition. So it looks a little bit scary, but it's very simple definition. For you guys, I think the best way to understand it, think of K as the class of rooted finite binary trees. Think of K as a class of finite rooted binary trees. So every internal node has either one or two outgoing edges. Right? So, and there is a natural, with every binary tree, you have a natural function, which is the height of the function, of the tree, that is the length of the maximal path. So suppose you have a class of finite structures, and suppose you have a computable function that associates a number, a natural number, which is called the height of the structure from K. And you say it's a height function if the following properties are satisfied. So what I'm doing is I'm giving a numerical value to every structure, finite structure. So we can compute the cardinality of all structures of height I. That's the first property. So when I say the input to H is a structure, so you're actually looking at the open diagram of the structure. You know everything about the structure. So its index. So its index is given a strong index is given. So the second property says, maybe I draw. So here is a structure of height I. So this is A. And the second property says, basically, you can collect all substructures of height I minus 1, and that collection is contained in of height at most I minus 1, and that collection is contained in a substructure of height I minus 1. And this is unique. So the second property says the substructure of height I minus 1 guarantees that this property that it's a unique property. It's a unique substructure. So if you think of the trees, it's basically if you have a tree of height I, there is a subtree of height I minus 1. Right. So and it's the largest subtree of height minus 1. And the third property says basically the height function doesn't behave badly. So I don't want to have a structure of height I such that if you take a subset over here, which is outside of the substructure of the largest substructure of height I minus 1, so C, and combine the substructure of height I minus 1 with C, I don't want the height of it to increase to become greater than I. So basically, take a substructure of height I minus 1, the largest substructure, it's unique. Take anything which is left over, any subset which is left over, take the union. And there are two cases. The union is in the class K or not in the class K. In case it is in the class K, I want this height to be I. So this is a natural condition. And interestingly, so I came up with this definition when I was reading Hrushevsky amalgamation construction. So what he does with every finite structure, he associates some kind of numerical value. And his definition is sort of internal definition. So you have classes of finite graphs in every graph. So you have some kind of function which depends on the number of vertices in the graph and edges. And that function associates some kind of natural number associated with the graph. So I came up with this definition. Basically, that was inspiration. So his work was an inspiration. By reading his paper was inspiration to give this definition. OK. So now, why is this good definition? So one is any two structures from, I'll be giving you lots of examples of these classes. If you take any two structures from class K, then they're isomorphic if and only if they have the same height. And so I call them slices. So the substructure of height, the largest substructure of height I minus 1 is called the slice. And all the slices are pairwise isomorphic. So if you think of the tree of the subtrees of height I minus 1 isomorphic, or all the subtrees of height I minus 1 isomorphic. But more interestingly, every embedded system of structures from the class K is strict. Right? So embedded system is strict if the direct limit does not depend on the embeddings. So over here, so existence of a height function actually guarantees that if you take a limit, it's whatever it is, it's always strict. And the reason for that is Koenig's lemma. So you take two limits, and you take level I, and you look at all isomorphisms from the first limit to the second limit, and the isomorphisms, they map the substructures of slices, substructures of height I to the substructures of height I, and there are only finitely many of them. And then you involve the Koenig's lemma, and you can construct the isomorphism between any two direct limits. Okay, so are you okay with that? So that's intuition. This implies that here's now the B class, the branching class. The class K is called the branching class, or B class for short, if for any structure A of height I, there are two distinct substructures in the class K, such that their heights are greater than the height of the class of A, of the structure A, but at slice I, so the B and C, these two extensions coincide. So you take a structure, basically there are two extensions, which are not isomorphic, but which agree on the structure at the height of the original structure A. Okay. So here are the examples. I'll give you now plenty of examples. So the first example is the trees of bounded degree D. The height function is the height of the tree. So that's a branching class. Pointed connected graphs. So you look at all connected graphs, but there is a point there. So in the signature, you have pointed connected graph. Signature contains a root. You can think of it the root. And the height is basically the distance from the root to the border of the graph. Right? So the height function is the max distance from the root P to the vertices of G. So you need to put one condition, that is, if the height of the graph is I, you want to put a condition that there is a vertex at height I whose degree is less than D. Right? So and that guarantees the class is going to be branching. If all the nodes at the border at height I have degree D, there is no continuation. So you don't want that. So you need to do a little bit that thinking here. Relational structures whose Geifman graph is a connected graph of bounded degree. So that's also branching class. So you can have a partially ordered sets with the minimal element. So the partial order P is the minimal element. They see the covering relation. So the Y covers X if Y is greater than X and there is nothing between Y and X. And what condition here is that each X in P, in the partial order P, has at most D covers. So D is fixed. So this is a small I consider the small finiteness conditions. We have these here, and this seems to be sort of a natural condition to somehow introduce randomness. And the examples of classes of this type, there are many, many structures where this D somehow comes into play. So the class of delta hyperbolic connected pointed graphs, hyperbolicity comes from group theory. There is the concept of hyperbolic groups. So here is the graph. So delta is given. You pick up 3 points, x, y, and z. So you pick up the shortest path from x to y, from y to z, and from x to z. And the graph is delta hyperbolic if delta neighborhood of any two sides, so of this triangle, cover the other side. So basically, triangles are very thin. Delta is thin. So that's a definition of hyperbolicity. So these hyperbolic graphs are the connected pointed graphs of bounded degree D, the class of binary rooted trees. So the difference between 1 and 2 here is that I'm ordering the children of nodes. So there is order here. So it's not just a successor tree, but there is order on the nodes. So there is an extra predicate. Here's example 7. It's a bit different from all the previous examples. It's n-generated universal partial algebras. So that is, n is fixed here. That is, you have n number of generators, fix them in the signature. And consider all finite partial algebras of the signature, and the height function is the maximum among the heights of the shortest term representing the elements of the algebra. So you pick up any element, it's generated from the constants, and there is a term that represents that element, and you pick up the smallest term in terms of the height, and that's the height of the structure. So the sparse graphs, so the class of AB sparse graphs, connected pointed graphs, and graph is sparse if any subgraph of G with M vertices at most AM plus B edges. These are examples, and the point here is you're the one who actually create the structures with height functions. So if you want to create some kind of structure, some kind of classes, you're the one who create it, and you can define heights. So it's under your control. So what is good about these now branching classes? Well, they define trees, right? So you take a fixed branching class, and the root, it's an empty set. So every node is going to represent a structure in the class. The root is the empty. So you can assume that K always contains the empty structure. This level is -1. And nodes at level n are the structures of height n. So, and because the height function is computable, so this is a computable tree. At level n, you know how many structures sit, right? And that's h of, so h n, so minus 1. So, and these are all structures of height n. And this is a tree. The reason for that is if there is something which combines here, so this is a structure in K, and this is the level I, for instance, I. So the second condition of the height function guarantees that there is only one largest I substructure. So it's not possible, collapse is not possible. You're actually building a tree. Right. So let B be a structure of height n, the successor of any structure C of height n plus 1. Its successor is any structure C of height n plus 1. So this tree doesn't have dead ends. Any questions on this? It's a computable tree. So this is a, where did I put? Okay. And now we're in good shape. So we have a tree, we have paths, right? So given any node of the tree, we can effectively compute the structure B sub x associated with the node, and we know the height of it. Each x has an immediate successor. We can compute the number of immediate successors. So it's a computable tree. And now you can look at all the limits. So the class, let K be a class, B class, branching class. K sub omega is the set of all infinite structures which are direct limits from the class K. And we call this class, I'm going to call this class a B class as well. So. And there is a correspondence between k sub omega and the set of all paths through the tree. Every path determines the limit structure, and the mapping from path to its limit is a bijection. So you need to think a little bit about this. It's not trivial. It's not so trivial. So it looks trivial, but it's not. Because the limits, when you take the direct limits, they don't have to be on the same path. Right? But the reason so this works is because for every I, you have only finitely many structures of height I. And that basically gives you this bijection. So there is a naturally defined topology. You take a node, right, and look at all the extensions of the structures, infinite extensions of the structures which go through the node, and that's called a cone. And this is a set of base open sets, and these are the base of the clo-open sets. And the node, which sits on the tree, is called the base structure. So you have a tree. This is the cone, and it's x. Sometimes I denote it by bx, and sometimes I denote it by a sub x. So this is the base of the cone. And there is a naturally defined measure. So measure is defined by induction. Right? The measure of the root is 1. So if you know the measure of the cone at point x, and suppose the measure is 7, and suppose it has 49 successors, so then you give to each of them 7 divided 49. The measure is going to be that. And it's also a metric space, naturally. So you look at two structures, A, B, and you look at which the maximal level where they agree. And you look at the measure at that level, and that's a metric space. That's a metric, and it turns the class k omega into the metric. So k omega is compact, is countable and dense. Finite unions of cones form clo-open sets. In the topology, the sets of all mu measurable sets is a sigma algebra set. And here we axiomatize the notion of randomness for structures, right? So a structure is random if it passes every ML test, and you immediately get the continuum property, that's abundance. The number of Martin-Löf random structures in k omega is continuum. In particular, for all examples, 8 examples I have given, we consider the classes contain continuum Martin-Löf random structures. So, but interestingly, if you look at those definitions, everything depends on the constants. So you have the pointed. So if you have a graph, so if you change the point, you switch the tree. You change in the tree in some ways. So the question is whether this definition is dependent on the constants. And it turns out so because of boundedness and because the distance between any 2 points is finite, any open set in one topological space can be transformed into the other. And in particular, any Martin-Löf test in one topological space can be transformed into the other. So for all examples of classes, in those examples, Martin-Löf randomness is independent on the choice of constants. So randomness is isomorphism property. So that's what we wanted, right? So the proof is not trivial. You need to do some work, but it's technical and not how I'd say. It's randomness for reals is independent on the base. It's very similar to that. So randomness for structures is independent on the generators. So here the summary is basically, if you want to talk about randomness, you need to say where you are. You need to define the context. So if you want to talk about randomness in groups or in classes of groups, you need to say what classes you're interested in. So also, it's up to you to define H. So this is lots of flexibility here. And the measure is, I would like to give you one interesting thing here. So the measure, I define the measure in a very particular way, and it's in some way, it's a rude way of defining the measure. So say, for instance, you have the class K is rooted trees, binary rooted trees. And say, for instance, you look such that every leaf has at least one successor. Let's look at this tree. So the height of this tree is 1. Right? How many extensions do we have? So we have 3 extensions. Right? One extension is this. The other extension is this. And the third extension is this. So if the measure of this cone, of all the structures above this binary tree is 1, so my measure, so the measure I define is 1, or gives the measure to this, to the cone based on this structure is 1 over 3, 1 over 3, 1 over 3. So this is how we defined. But, well, the slides define. But if you think about it, the probability that this structure occurs is higher. So it's actually, so if you look at this, for each node, think of it, you're tossing a coin with side 1 and 2. If the side is 1, it means there's only 1 extension. If the side of the coin is 2, it means 2 extensions. Right? One possibility is this. Another possibility is this. Third possibility is this. And fourth possibility is this. So you have 4 possibilities, but these 2 structures are isomorphic. Because so the probability that this occurs is higher. So it's half. My definition gives 1 over 3. So this is sort of not algebraic definition, while this is an algebraic definition. And that's why the way you define the measure is also important. So this is sort of 1-step extension of the measure. You can do 2 steps, 3 steps, and so on and so forth. Okay, so that's already an interesting concept. So, yeah.
So you're saying that if you take the structure in 2 different measures, defined in these different ways, typical random structure?
Yeah. So there could be randomness with respect to one measure, cannot be random, doesn't have to be random with respect to another measure. So it depends on you how you define the measure. And so my definition of measure is, in a sense, if the structure is rigid. So if the constant, for instance, if you look at finitely generated algebras where the constants are in the signature, then every finite structure is rigid. So my definition in that case is fine. But if you look at the trees like this, I don't know which one is better. So it's up to you to define. Okay, so, and I like it. It gives you flexibility. So you can embed sort of algebra a little bit, automorphisms of the structures a little. So now, what is the connection to computability now? So the infinite structure is computable if it's isomorphic to structure with domain omega, such that all atomic relations and operations are computable. We all know it, this definition. But here's one example I give. A structure is strictly computable if given I, you know its ith slice. Here are examples of strict computability. Every computable finitely generated algebra is strictly computable. So if you take a finitely generated algebra with the constants in the signature, if you want to know its ith slice, the only thing you need to do is you need to list all the terms of the signature up to height I and consider their values, and you define the I slice of the structure. A computable pointed graph of bounded degree is strictly computable if and only if there is an algorithm that given V computes the number of its vertices adjacent to it. Okay, so a computable rooted tree of bounded degree is strictly computable if and only if there is an algorithm that given a node V computes the number of immediate successors, computable, and so on and so forth. So if A is strictly computable, then it's not Martin-Low random. The reason is, so here's your tree. I mean, it's obvious. Here is your path. And this is your structure A sub eta. Eta is a path. Suppose it's computable. Because it's strictly computable for any I, you know where you fully know its diagram. And now you can look at this Martin-Low test. So the cones, and the measure of the cones goes to 0. So in particular, if the structure, for instance, in the graph case, if A is infinite pointed graph or tree or partial order of bounded degree, if A is computable and its existential diagram is decidable, then A is not Martin-Low random. So that basically it says that somehow so this sort of gives an intuition that probably you can have computable random structures. Right. Here's a bit more about it. So, let me, yeah. So we can prove that every B class contains Martin-Lev random structure computable in the halting set. It's an obvious thing now. So you just take, look at the Martin-Lev universal test. Look at the U1, U0, U1, U2. You look at U1. You look at its complement, and all the structures in the complement are structures are passed through a computable tree. The leftmost path in that tree is a random, and it's computable in zero jump. And the rightmost path is also. So I'll go. There is a reason I'm mentioning the rightmost path. We usually talk about leftmost. Rightmost path is also computable in zero jump. In particular, all examples have Martin-Lev random structures computable in the halting set. So here's now the view, like construction of the structure from the path. If you know the path, and knowing the path means at any I, you know the I slice of the structure. Knowing the path, if you know the path, you know the structure represented by the path. But how about the opposite? Suppose you know the structure determined by path. Well, can you actually compute path from it? The answer is no. To compute the path from the structure, you need to compute each level. In other words, computing each level from the structure requires you the jump of the degree of the structure. And that's where you can play to construct a computable structure which is random. Okay, so and this is what I'm going to do. So there is a B class S. So we're in good shape. It's up to me to define the class. Right? There is a class S, branching class, such that the class of limit structures in this class contains a computable structure which is random. And the proof is, I have enough time. So the proof is, I want to define the class S. What is the class S? My class S consists of binary trees, ordered binary trees. But not only that, I'm going to put a bunch of conditions on the trees, ordered binary trees, to get into S. And here are the conditions. All leaves of B are at the same level. So if there is a leaf at level, all the leaves are at the same level. They're all either on level 1 or all the leaves at level 2 or 3. If V has the right child, then all nodes left of V on the V's level, including V, have both children. If one node has two right child, then all the nodes on the same level have both children. Right? At each level I, there is at most one node such that it is the left child of its parent that does not have a right child. So basically the picture, my trees look like this. So all the leaves are at the same level. Now, if you look at its parents, so if some of the parents have the right child, then all the guys below have left and right child. So if there is a leaf which doesn't have a sibling, then it's only that leaf is unique, one, and it is the left child of its parent. So that's something like that. Now, if you look at tree like this, which belongs to the class, there are two possible extensions of it, exactly two, which belongs to the same class. One extension, I just copy this tree, and to each leaf I put this. And the other extension is this. So I pick up the rightmost leaf, and I don't create the right child of it. So every tree here in the class S has exactly two extensions. So the tree T of S is just a binary tree. Okay. So, and now we're sort of in a good shape. If B belongs to S, then it has height n, then there are exactly two non-isomorphic extensions of B of height n plus 1. Both are in S. Hence, the tree is isomorphic to the infinite binary tree. For every n, the set of all trees in S of height n form a chain of embedded structures. So if you look at all the structures of height n, they're embedded from left to right. That's an algebraic property of the tree I'm building. So I'm putting, in addition to I'm putting a nice conditions on the class of structures. So for every n, the set of all trees of height n form a chain of embedded structures. And now, so it's an algebraic left embedding lemma, which says if x is lexicographically less than y, then you look at the length of x and y. If the length of x is smaller than y, then the structure associated with x can be embedded in the structure associated with y. So basically what it means is, so the lexicographical order is a nice one. So if you take a structure which corresponds to x, if you take a structure which corresponds to y, and x is less than y lexicographically, then the structure which corresponds to x is embedded into y. Right? And now we're in good shape. Consider omega. So it is left CE. Take its limit. Each limit is a structure. And each structure is, so this lexicographical order corresponds to embedding. This is a computable sequence. So the limit structure is omega. It's a computable structure. You got a computable Martin-Loaf random structure. Any questions on that? So this is a sort of, I'm exploiting the definition in some way. So this is the fact. So if you think of the random omega, if you look at position I, you don't know what happens there, 0 or 1. So the situation here is very similar. If you pick up a vertex V, and you want to know whether there is outgoing edge 1 or 2 outgoing edges, you don't know. So if 1 appears, that you don't know whether there will be 2 outgoing edges from that. And now, so what I would like to do is I would like universal, I would like to go back to structures which are strict in a sense that for any I, you know the I slice of the structure. Right? So no universal computable finitely generated algebra is Martin-Loaf random in any possible class. So I just proved it. So if you have a computable structure, but algebra, universal algebra, so it's all the operations are functions, and you have finitely many generators, and generators are into constants. Then the algebra is not Martin-Loaf random. Well, in any such class which consists of algebras, universal algebras, there is a algebra, Martin-Loaf random algebra, which is computable in a halting set. One way to refine it, to ask the question whether there is algebra where the word problem, so the equality is CE, or equality is co-CE. Right? So you take a finitely generated universal algebra, it's called CE if the word problem in A is computably enumerable, and it's called co-CE if the word problem is co-CE. And I'm not talking about operations here. The reason for that is every element of the algebra as a representation is a term. And what I'm saying is, and the operations on terms, basically it's, operations are vacuously computable there. All right, so it's a, okay. Any questions on this? So elements are terms, and the equality is between the terms. That's what is happening. So the question is, well, are there computably enumerable algorithmically random universal algebras? Or algorithmic random co-CE algebras? So there exists a branch in class S. Again, I'm the one who is creating the class, right? That contains co-computably enumerable Martin-Loaf random universal algebra. So I'm not going to describe now the class, but I give the intuition here. So the intuition here is I'm going to construct a class of partial universal algebras such that the following properties hold. At every level, n, there are exactly 2 to the n algebras. So I want the tree to be binary tree again, right? So, and lexicographical order, I want to satisfy the following properties. So if you take two nodes in the tree of the same height, and if x is less than y, then the structure which corresponds to x is a homomorphic image of the structure which corresponds to y. So if you move from right to left, you're just squeezing the structure, you're making it smaller, smaller, smaller. You're making it homomorphic, right? So you have a structure here. This structure is homomorphically mapped into the same structure, which is lexicographically less than it. And this is homomorphically mapped to the same structure, to the structure, homomorphically mapped to the structure on its left, and so on and so forth. So when on the tree, you move from right to left, you're taking the homomorphic images. Or when you're moving from left to right, you're splitting the equality relation. Splitting equality relation is co-CE. Right. And now you take omega. It's left CE approximation. Take its left CE approximation. This corresponds to the sequence of partial algebras. Each AXI is homomorphic image of AXI plus 1. Some equal elements on the right side are split and become non-equal on the left side. No, on the left side, they split on the right side. And once they split, they stay split. So co-CE. And now if you look at the limit of this structure, so you need to do a little bit work, but it's, so that basically you need to look at the subalgebra generated by constants in this limit. Then you get a co-CE algebra, which is Martin-Lefrandom, which corresponds to omega. And here's the play why you need the rightmost side, right? So there exists branching class S omega that contains computably enumerable Martin-Lefrandom universal algebra. So equality is CE. What you take 1 minus omega. It's the right side of the computable tree, right path. And it is the limit of sequence from right to left. While you move from right to left, you're taking homomorphic images. Once you put two elements, when you glue two elements, they stay glued forever. And you get a CE algebra, which is Martin-Lefrandom. So now I want to say, I have 10 minutes. So the degrees of Martin-Lefrandom structures. And there are a couple of interesting things happening here, which is you take, well, the degree of the structure is, you look at all copies of the structure, you look at all the degrees, and if there is the smallest one, it's called the degree of the structure. Right? That's the standard definition. So if the class jumpless, that means if every path through, just a minute, if every structure in K omega computes its path, then you call it jumpless. So that is, jump is not required to recover the eta. So you don't need to have jump. That's what it means. So if K is jumpless, then every structure in the K omega has degree. It's obvious. And the degrees of Martin-Lefrandom structures are precisely the Turing degrees of random binary strings. So jumplessness is a nice property in the sense that basically if you're jumpless, then you're in the category of Martin-Lefrandom strings in some sense. But what happens if you're not jumpless? Just examples of algebra. And this class is left algebraic. And that's, if you look at this, where is the algebraic left embedding lemma? So when the way we constructed computable structure, computable Martin-Lefrandom structure, was that we put nice conditions on the class K. And what I want to do is I want to basically formalize this lemma and to put it into the definition. Left algebraic if there is a computable ordering on the elements at each level such that the induced lexicographical order, we have the following. If you have a path, and if you have any approximation to the path, then that computes a copy of which is represented by the structure. So if you have let's see, if you have a path eta and you have approximation to it, then from the approximation you can actually compute a copy of the structure. Right? And in some ways, in opposite, if you have a path and you have a copy of the structure which corresponds to the path, then you can compute its approximation to the path. And the example of a computable structure, which is Martin-Löf random, and the class in that example satisfies these properties. And now you have the following dichotomy theorem. So suppose A is a Martin-Löf random structure in the left algebraic branching class. And suppose it has a degree, then the degree is either computable or halting, or solves the halting problem. Right. And it's sort of a nice theorem in a sense. The proof is sort of providing that structure which computes whose degree is computable and halting structures whose degrees are computable and halting are easy. Look at the leftmost path. It is approximable from the left, and that's a computable structure. So its degree is computable. Look at the rightmost path. If you look at the rightmost path, so now you do a little bit of reasoning and show that the rightmost path, the structure which corresponds to the rightmost path, solves the halting problem. And to show that nothing else is possible, so you need to do some forcing type of arguments. And that's where the done came into play. So done provided a couple of really, really nice lemmas, which allow to actually show that this is dichotomy theorem. So, and finally, so this is the final part of my talk. So this is also interesting because, so it refers to the question that I asked at the start. What about finitely presented algebras? So class of universal algebras is variety. It's a standard model theoretic definition. It's classical. So, but Melnikov likes to use the word classical or classic. So it's variety if it's closed under subalgebras, homomorphisms, and products. Varieties are defined by, axiomatized by universally quantified equations. An equation is just the equality between the terms. And you say that the equality is non-trivial if it is non-trivial. That is, if at least one of them contains a variable and they're not syntactically equal. Right. The class of all, so now I'm looking at all algebras finitely generated, universal algebras, all, in the class of all algebras. So the class of all infinite and generated algebras that belong to a non-trivial variety has an effective measure 0. Non-trivial proof. So you need to walk through, you need to actually construct a Martin-Löf random test. You need to show that the measure of the set is effectively 0. You need to do some universal algebra here. And hence, no finitely presented algebra of non-trivial variety is Martin-Löf random. It is in the class of all universal algebras. That's important. It is potentially possible, for instance, to look at the class of all groups with specific type of groups. And in that class of groups, it could be, you could have a finitely presented group which is Martin-Löf random. So it depends on the context. Context here is algebras, all universal algebras. Okay? So in particular, no finitely generated Martin-Löf random, Martin-Löf algebra exists that satisfies a non-trivial set of equations. So if you have an equation, non-trivial, if you have anything that satisfies it, it's not Martin-Löf random. Right. So, and that's, so basically this answers our question. So
you said we could interrupt.
Yeah.
What about free groups on n generators, among groups on n generators?
Yeah, the free group is computable group.
Yes.
So it's a strict group. So that's, you know the level. And that's why in the class of all groups, the free group is not Martin-Löf random. Any computable algebraic structure is not. Any finitely generated algebraic structure, in particular computable structure, in particular group, free group, is not Martin-Löf random in any class.
In the class of all.
In any class. Any class. Because it's computable, because it's strict. You know the levels. So if you're in the class of strict structures, where from the structure you can compute the path, then you are not random in any world. Okay. There are lots of questions. Assume that B is neither strict or no left algebraic. What degrees can be realized in ML random structures? Here is an interesting question. So for me, as a sort of who is interested in computable model theory, so if you look at the class of all random strings is equivalent to the class of all by infinite random strings, whatever equivalence means. So anything you do in the class of strings can be transformed in some ways into the class of by infinite strings. But if you take any two by infinite random strings, they're elementary equivalent in the first order logic. Right? So in particular, the first order theory of any Martin-Löf random by infinite string is decidable. So in that sense, we guys we're studying a theory, non-trivial models of one theory, decidable theory. So that theory doesn't have a prime model, doesn't have a saturated model. But if you fix a constant, there are uncountably many one types provided by, for instance, Martin-Löf random strings. So what I want to do is whether that is true in the general case. I don't know. Dan and I, we tried to prove it. We thought we proved it, but we couldn't do it. Is the first order theory of Martin-Löf random graph of bounded degree decidable? So intuitively it should be, because everything should be realized there. So you say any graph is there, but you need to construct. So I don't know how to prove it. So are two Martin-Löf random graphs of the same bounded degree elementary equivalent? Another interesting question is, I want to go into groups. So construct B classes of finitely generated groups. Masnikov, he almost always claims, he claims that there are plenty of examples. For instance, finitely generated delta hyperbolic groups are B classes. That's what he says. I don't know. He says the proof is complex. I don't know. So this would be a nice, so you would be in real algebra. So other computable Martin-Löf random graphs in the class of all connected graphs. I specifically constructed a graph in a specific class. But in the class of all graphs, it seems there are problems because the class K sub omega is complex. You don't know how to handle, so we don't know the measure. We don't know how to compute the measure of things, generally, graphs. Here's interesting. So you look at the class of all subgroups, non-trivial subgroups of the additive group of rationals. We know algebraic descriptions of this. Now, it would be nice to actually turn this class into a branching class. And then it would make sense to talk about Martin-Löf random groups, subgroups of the group of rational numbers. I don't know whether it's possible or not. But it seems this is a natural thing. So every group here is determined by primes. And those primes through those primes, somehow you should be able to define the height. And the height is under our control. If we probably do it properly, most likely it's possible to show this class is branching class as well. So, and here I finish talk. Okay, thanks.
Any questions?
Did you look at other sorts of tests, such as P-move?
No. You're welcome to do it. So there are lots of things to do there. Yeah.
There's some version of Schnorr-Levin theorem for universal. Randomness using initial segment complexity or something.
Dan and I, we thought about it, and he was saying that it is almost trivial to do it. I don't know what he meant. He said that just you can code the whole thing into binary things, so I don't know, somehow. So he was saying that it's possible. Yeah, I don't know. I don't know. That's why I'm saying I don't know.